16.9 today, and this is the divergence theorem. This is Gauss's theorem. So this is finding the flux of a vector field that crosses some surface S. So it is a surface integral of a vector field, but this is particularly for closed surfaces. So I want to point that down right now. That everything we're talking about today will be for some closed surface. Some closed surface. Some solid region with a closed surface. I can even write that. Everything is for something. It's a solid region with a closed surface. So before we found the flux of some vector field across some surface, last thing we did in our last lesson was we dealt with a paraboloid, and there was a top disk like this. And with the top disk above the paraboloid surface, that would be a closed surface. So some examples of what we're talking about. What would be some closed surfaces, like a solid region with an entire closed surface? The first one, probably the most popular, is a sphere. Right? There's a solid region with a closed surface. Well, what about a paraboloid that went up like this along the positive z-axis? Well, that just keeps opening up like this. So that wouldn't be closed. That would not be a closed surface. Unless you had a disk at the top that bounded this. Now it would be a closed surface. Does that make sense? Or think of a cylinder. And some cylinder like, how about x squared plus z squared equals 9? Think of that cylinder. Well, that cylinder would just be centered on the y-axis, right? But doesn't it go on infinitely? Doesn't it just continue on infinitely? Well, this could be a closed surface if we said only do this from, let's say, 0 to 4 for y. And then we stopped here to and the closed surface would be including this disk, and you would have outward, which is called positive orientation. All the normal vectors off there. Outward orientation, normal vectors off that surface, and then off the lateral portion of that cylinder. Now you would have a closed surface. But you'd have to be specific and say including these disks, including the disks at the end. Both disks, at this side and this side, at y equals 0 and y equals 4. Here you get including this disk. And this theorem, Gauss's divergence theorem, is for outward orientation, which they refer to as positive orientation. But what's so awesome about it is when we did these problems, the last problem, it took a long time to deal with finding the flux off that surface, finding the flux off this surface. We had to add them together, right? This is going to be a one-shot deal. Gauss's divergence theorem. It is rock and roll cool because you can get it in one shot. The entire flux across the entire surface, all portions with outward orientation. So these are common examples. What? The sphere, maybe a paraboloid includes a disk, a cylinder that includes this disk and that disk, all closed up. One more. How about like a rectangular prism or a cube? How many sides does it have? It's got 6 sides. So if I did this the previous way in section 16.7, I would have to compute six fluxes, right? 6 surface intervals, and add up all those together. This is going to knock it out of the park in one shot. So if you want to put that image in your notes, you can, but stick normal vectors off each side. Be like, okay, we oriented outwards, so we get all these 6 sides coming out this way, coming out the other way, etc. So that's what this theorem is for. But it's only for what? When you have a closed surface. This isn't going to work like the problem we did yesterday. I think it was just we had a parabolic cylinder, and we just got the flux off the top. Well, that's not a closed surface. Cool. So to begin, what we should do is we should start with a problem from yesterday. Then we'll jump right into Gauss's theorem. So I'm going to start with, this is at number 2 problem. And it says, all right, let F equal. Here's the vector field. The vector field is 3x, y, y, and 2z. Well, consider the boundary surface of the cylinder. And if you just don't want to write all this out, you can use this document right here with the number 2. For 0 less than or equal to x, less than or equal to 4. Okay, that's the cylinder centered on the x-axis, right? With outward orientation. Outward orientation means positive orientation. All the normal vectors will be oriented outward along the surface. They say compute the flux of F. Only out of the disk at x equal to 4. So, and that would be in which direction? That would be in the direction of the positive x-axis. Okay. So, if you don't mind, let's draw an image of this. Y-axis, Z-axis, and here's that x-axis. We're talking about just a circular cylinder. Goes from 0, 1, 2, 3, 4. Just right there. There's the cylinder. But we're only getting the flux out of where? We're not going to use Gauss's divergence theorem now. We're only getting a flux only off that disk. And it's going to be oriented outward, which means, you know, which way do you mean outward? In the direction of the positive x-axis. So it sounds like we're not going to use this. We're not going to use Gauss's divergence theorem. But that's good. This is a good warm-up. Let's go back to how do we find the flux? It's a surface area. That's equal to F dot ds. We got a nice vector on that, and this is equal to F composed of some surface. Now, I want to think how you want to project that. Couldn't we project that onto the YZ plane? So I'm going to write R composed of Y and Z, our surface. Then it's a dot with the normal vector. RY cross RZ. And I'll put DA, and this right here is just going to be that region D. Or, maybe here we'll use RZ cross RY. It depends. Which one do we want? We're going to use the one that gives us the outward orientation. Okay. So, I'll start out. I need the orientation coming outward. So the hardest part is parameterizing that surface. Let's parameterize that surface. R of
X.
Is it X and Z or Y and Z?
Y.
Here's the hardest part. Can you help me parameterize that flat disk? Alright. Hope it's not too hard. Z equals Z, Y equals Y, what goes here? Well, it depends. What's that number?
4.
4. Ta-da! That's very important. We are going to parameterize that surface right there where the disk is. You go, wait, but that would mean an infinitely long plane, right? And x equal to 4. Yeah, but it's going to get restricted to the disk when we do this. Cool? Hey, so let's check it out. Like, what's RY? What's RZ? This is rock and roll. Some people already know the normal vector. Does anybody know a normal vector that comes off here? Unit normal vector? The unit vector that's a normal vector and goes in that direction?
1, 0, 0.
You got it? He knows it. That's what's going right here. I'm going to put it. Brad, very good. He knows this is going to be 1, 0, 0. He knows that. So it's got to go in the direction of the positive right there. But I thought we'd play it out and see it. What's this? That derivative is 0. What's that derivative?
1.
That's a 0. What's the respect to z? 0.
Zero.
What's the respect to z? 0.
1.
Alright, what's that cross product? See, I want to make sure. We're going to use ry cross rz or rz cross ry in terms of partial derivatives. When I cross these, I get 1 minus 0, 0 minus 0, 0 minus 0. Yes, this is what we're going to use. We're not going to use the other one. The other one would have been pointed in the other direction. And they want it in the direction of the positive x-axis. So we got this parameterized. Let's rock and roll and hit this the amount of part. What goes here? All right, I'm going to put it out here. I've got enough room. I'll do dot with 1, 0, 0. dA. This will be just that region. This is, let me look at the vector field, a 3x, a y, and a 2z. But I have to have all this in terms of what? D, y, and dz, right? So you can think of this as dy, dz if you want. So can I keep that x? No, f composed of the surface. So what's going to replace that x?
12.
Yep, I'm going to put 4 in there. I'm substituting the x component into that. That's what this means. And what's 3? Let x equals 4. What do you get out of that? 12y 2z dot 1, 0, 0 dy dz. What's the dot product? 12 dy dz. So when I'm going to have to set up some kind of disk, you want to go polar on this, you got a faster way. There's a faster way. I could do polar coordinates, because it's that disk, is the projection onto the YZ plane. But if I take that 12 out of there, I just have what?
D.
I'm thinking this is still that region D right there. That disk. It's just that disk right there. But if I get the 12 out of here, this is just a 1. What's the double integral of 1 find?
Area.
Area. So I can just do 12 times the area of the disk. And what is the area of that disk? Well, we got to look at this carefully. The cylinder equation was y squared plus z squared equals 9. What's the radius right there? It's a radius of 3. That one, because it's that end of that, kind of capped off that cylinder right there with the disk. That radius is 3. So area of that disk, 12 times pi times 3 squared. What's 12 times 9? 185? And everyone, that's the flux. Only coming out of what? Right there. I did this on purpose. I wanted to start with this. Number one, let's review how to find flux across just one particular surface. But number two, you see how long it would take if you had to deal with that closed surface. That was only one portion. Then I'd have to do the other disk going outward. Then I'd have to deal with this one. I'd have to parameterize the cylinder portion, which is not so easy. This theorem will knock out of the park an entire closed surface. So guess where I'm going with the next problem? Same structure, same design, but not just only out of this. I'm saying the entire closed surface. Out of this disk, off this side, and above everything. So I'll rewrite this. Everyone, here comes our next problem. Is everyone okay with this? Yeah? Okay, cool. So I'll leave this, I'll erase this, but now I'm going to change this to same vector field, and I'm going to move on to number 3, which says compute the boundary conditions of the cylinder. surface S. So in parentheses, including the sides, the top, the bottom, etc. The reason I put that in parentheses, I'm talking about the flux off all of this. So outward here, outward off here, closed surface. So it's including the 4, including the 0, stopping it. And the flux off that cylinder with the closed outer. So in other words, when I say including the side, top, and bottom, I'm saying off this lateral portion and also off outside those, the flux across those discs. Well, then what can I do? That was enough just for one disc. That's a closed surface. We're going to go Gauss. We're going to use Gauss's divergence theorem. This is equal to the triple integral of the divergence of F, where there's our solid. This is the solid. E is the solid. And we'll just put a dV there for thinking of D in terms of volume. All right. Ready to set this thing up? Well, first we got to review divergence. What is divergence of a vector field? Does that find a scalar or a vector? Divergence of a vector field. Scalar finds a scalar. And what it is, I'll put it right here. We have to do del dot F. Well, what does that mean? Okay, it means we got to do ddx, ddy, and ddz dot some vector p, q, r. Like the vector field they got there. But do the dot product because it comes out really nice. This isn't a cross product. What is this? You're going to love Gauss's divergence theorem. This is just derivative of the p component with respect to x plus the derivative of the q component with respect to y plus the derivative of the r component with respect to z. All right, let's try it. What do I get? You ready? I know you can do this in your head. What's the derivative of x with x? Plus derivative of that with respect to y plus derivative of that with respect to z. I get 3 plus a 1 plus a 2. My gosh, it's a nice simple circle. Easy. All right. So when I get a 6 times a triple integral, here's E. Now I get that. This is super fast, isn't it? It really is. I mean, sure, if this got a little more complicated, I would deal with it. I get it. I would do the triple integral. Now, do you want to stay Cartesian? X, Y's, and Z's, we've got a solid going on here. Or you want to go cylindrical coordinates? Or does someone have another idea?
Can I just calculate the volume of the cylinder?
Brad, you're so good. So I could have gone cylindrical coordinates right now, right? Cylindrical coordinates would have been appropriate. Brad had a better idea. He says, well, since you got a constant out in front, there's no variables here. This is a triple integral 1. Triple integral 1 finds volume. He says you can just do 6 times the volume of that cylinder, and you'll have your answer. Now, the only danger with that, Brad, go ahead. The only danger there is what if a student didn't know volume of a cylinder, right? So that's one way. I'm going to do it first, and then I'll erase it. I'm going to go back and do cylindrical coordinates. In case someone in here was like, I'm not going to remember the volume of a cylinder. I never took a geometry class. So I'm going to do that. I like your idea first. He goes, it's 6 times the volume of the cylinder. What's the volume of the cylinder? It's I r squared times the height. I'm avoiding the integral. Mathematics. I'm avoiding doing the calculus here. But what's that radius?
3.
Great. What was the height, even though it's on its side? What was the height? How far did that, what was the height of that cylinder? 4, right? It was a length of 4 there. Brad, very good. That would be your answer. How much work did this take compared to the last problem, which only gave us the flux out of that one portion, right? I saw that highlighted from before. I'm talking about we got the flux off here, we got the flux off here. This theorem is awesome. What is that? What's 6 times 9 times 4?
216.
216 pi. That's the flux. Hey, I am going to go back in case, you're like, I don't know volume of cylinder. And I will go cylindrical coordinates, okay? So, what if I did cylindrical coordinates? Cylindrical coordinates is polar with another variable, right? 0 to 2 pi, what was the radius? 0 to 3? 0 to 4? What letter's automatic with cylindrical, just like polar? See, if I do cylindrical coordinates, I can't forget this letter. R, like RD theta. Now, what's my third variable? It depends. What was I using? These were x's, right? So it's not always z when you go to cylindrical coordinates. It was an x. This was x equals 0, so I'm going to write dx dRd theta. Because we had this, the reason this cylinder was on the x-axis. But I would just do cylindrical coordinates right there. But don't forget that r, you won't get that 216 pi. RD theta, just like polar. But see, some students prefer this because maybe they're not used to all these formulas from a geometry class. So I'll erase all that, but let's do this. We should get the 216 pi. Can I break it up? Split it up? Oh, you sure can. 0 to 2 pi d theta. 0 to 3 of an r. And then you got a 0 to 4 of dx. And we'll get the same answer. That's 6. That's 2 pi. What's the integral of r? R squared over 2. What's that become? 0 to 3 of r squared over 2. Is that 9 halves? 9 halves. And just 4. Now check it over. Do we get 216 pi? Yep, the 2's cancel. 6 times 9 times 4. Right? Pi r squared h. The flux. Isn't this theorem cool? I mean, you gotta appreciate it. Do an entire cube. Oh gosh, I don't have to do 6 separate double integrals like before. I get it in one shot with a triple integral. But that's Gauss. I mean, everyone know about the stories of Gauss, who was a child prodigy? Most of these brilliant mathematicians were. I mean, the story is, I don't know if it's true, but he was like age 10, and they had to add up the numbers from 1 to 100. Does someone know that story?
Yeah.
Who knows if it's made up, or maybe it's been exaggerated over the years. But the story's about Gauss, how smart he was. He's age 10, they were talking in class, the teacher goes, close your books, you gotta add up all the numbers from 1 to 100. It would have to take a while, you'd sit there and look. All that stuff, 4, 5, 6. 10 seconds later, his name's Frederick. Frederick's just sitting there staring out the window. And they're like, teacher went over to yell at him, teacher looks at his desk, and he has the exact answer. So how did he do it? He just, I wish I thought like this at age 10. He thought of, there had to be a pattern. He looked at it like this, and he looked at it backwards, just because he thinks that way. 98, 97, and do you see a pattern? Add down.
101, yeah.
Add down. What's that plus that? That plus that? What's that plus that? What's that plus that? What's 100 plus 1? So he knew the answer was a bunch of what? 101s. Age 10, I'm playing with Legos. Gauss is thinking like this. Child prodigy. So he knew the answer was a bunch of 101s. How many of them?
50.
Oh, it's 100 of them. But it's like, hold up. Not 100 of them, because this would be counted twice, so you had to divide it in half, which means divide out of 1. So 50 times 101, that's how he had this answer. matter of 30 seconds. Isn't that amazing? But that, I mean, that's the story. You never know if that's like, you know, it's a myth. It's been exaggerated over all these years. But just, this is a brilliant, brilliant theorem we can use. The divergence theorem by Gauss. Because it deals with closed surfaces, really saves us some time finding the total flux. Cool? Alright, we did a cylinder. What's the next one? Let's now do, oh, it's a box. Everyone, the vector field's a little different, so let me change this up. I'll erase all this. This time, I'll erase that picture. The vector field is yeah, we did number 4 is just an extra problem. Y minus x. A z plus 5y. And x plus 2y. Okay. What's S? S is the boundary surface. So this is what I mean when they say boundary surface. I want to highlight it in my theorem over here, where I wrote all this out. That's what one we're considering to be a closed surface. It's the boundary surface of this solid. Or the box. And that's 6 faces. Oriented outward. Bounded by the coordinate planes. And they've got x equals 1, y equals 4, and z equals 3. And thanks for being patient as I write all that out. I want to be very specific on what we're finding here. So we can draw that. Let's make an image of that one. Well, z goes up what, 3? Y is 4. X is 1. We're like, okay, we got it. We're going to go out 3. When we get the flux, I just like to draw pictures. So you go, where are we getting the flux off? Which side? All 6 sides. Off the top, off the bottom, off that right side box, off that left side box, off that other side, and off this side. All 6 faces. You bet. Let's do it. No Gauss. We're going to use Gauss's divergence theorem. Closed surface, solid region that it bounds. This S is the entire boundary surface. Divergence of vector field, ED. Now keep in mind, you could have done this the old school method of section 16.7 of doing 6 separate surface angles. But we're not going to do that here. This theorem is too cool. Alright, let's start with the divergence. I need to derive this with respect to x, plus the derivative of that with respect to y, plus the derivative of that with respect to z. What's the derivative of that with respect to x?
Y.
Negative 1. Let's do that with respect to y. 5. And derivative of that with respect to z. 0. dz, dy, dx. Negative 1 plus 5 is what? Cool. I'm going to label these. Z went from what? 0 to 3. The y went from 0 to 4. The x went from 0 to 1. If you want to put that 4 out in front, you can. You know it, everyone, if I got like little variables in here, we've done triple intervals before. If I got variables in here, I can integrate this separately. I can break them up if needed. Brad, can I do it here too?
Yeah, you can do volume.
And volume of a box is pretty easy, right everyone? I'm just going to do 4 times volume of box. Keep in mind, if I did get some variables in it, the vector depends on the vector field. The divergence of F, vector field F came out to have some variables involved in there, then I would have to do the triple integral. Maybe as an iterated interval, or I could split them up. But this 4 times volume of the box. What's that volume? Length, width, height, right? And what do you get?
48.
48? That's your flux. Hey, if you did a problem, you did a bunch of problems in the textbook, section 16.7 did have a problem where they wanted you to do what? All 6 faces separately. Doing them all. But you would get this 48 again if you add them all. The flux across all 6 surfaces. Cool. Alright, we did the cylinder. We did the box. What's another popular closed surface that we had drawn up before? A sphere? Alright, let's do a sphere. Okay, go in here. Now we have to calculate the flux. What you're going to calculate the flux? That's what we did in the last one. This was the surface. So when I noticed, when I just wrote all this out, I never even wrote that. What do you got to find? We were calculating the flux of F across S, the surface. And that was all that. So before I erase this, if you wanted to include that in your notes, go right ahead. That was the directions to the problem, okay? I just noted, like, what do you want us to do? Well, we have to calculate this. And that is the flux. It's the surface interval of the vector. All right with that? Let's get this out of the way. I'll keep that up there. I'll keep that up here. Here's the vector field. Force cubed. Plus 4y cubed. Y cubed plus 4z cubed. And 4z cubed plus 4x cubed. S is the entire surface. I only have to put the word boundary here because it's a sphere. For the sphere, with the center being the origin, and radius 2. Oriented outward. All right. Let's do this. Let's imagine doing this like in section 16.7. We did this like in section 16.7. We'd have to parameterize this surface we're talking about, which isn't so easy, which is the sphere. We have to parameterize. That would be a pain, but let's draw a picture of this. Z-axis, y-axis, x-axis. We got a sphere with a radius of 2, right? You go 2 that way. Now, I like to draw little normal vectors off this thing. Outward. Outward orientation. Off the entire sphere. The entire surface. Can we use Gauss's divergence theorem? You recognize it. Yes, that's a closed surface, right? Bound in some solid region. Has the entire boundary surface closed off. They call it a closed surface. See, the difference between closed surface and open surface. A paraboloid's an open surface, unless you cap it off somewhere. A cone is actually an open surface. It keeps opening up forever, unless you stick a disc at the top somewhere and cap it off. Same thing with a cylinder. A cylinder is an open surface, unless you knock two discs at the end and close it off. That's what we mean when I'm saying closed surface. The entire boundary surface. Taken care of. That's what's great about this. All right, so let's go Gauss. Gauss's divergence theorem. All right, check one up. Divergence vector field. This is E. E is the solid. That's E right there. This is E. When you see that E, go, what is E? We're talking about that solid region right there. E is that sphere, that entire solid. Solid. Well, let's start with the divergence value. I'm going to start filling all this junk in. Sound good? What's the derivative of this with respect to x?
12x squared.
Okay, 12x squared. Plus the derivative of x to y?
12y squared.
So y squared. Plus the derivative of x to z.
12z squared.
That's all z squared. Okay. Now, you want to stay Cartesian or do something else? Your call.
We can take the 12 out, right?
Let's definitely take the 12 out. Brad, our shortcut's not going to work this time. And Art, great call on taking that 12 out. It helps us see the problem a little bit more clearly. You want to go Cartesian?
No, that's polar.
No way, not with that sphere. We'd be a bunch of radicals, wouldn't it? So when I'd have to think, you know what the equation of a sphere is with a radius of what, 2? Look at this daggone thing. You and I would be sitting here. Solve for z, square root of 4 minus x squared minus y squared. Stick that up here. What would be the bottom region? Negative square root of 4 minus 5. What coordinates would you want to do?
Spherical.
Let's go spherical. So we went Gauss, now we're going spherical coordinates. All right. Isn't it cool how often these previous sections come into play? Well, here we are at the end of Calc 3. You're like, oh yeah, now we can go spherical coordinates. So, keep that 12 out there. But look, I've got enough room here. What's the volume element for spherical? Remember with polar and cylindrical, it's the r d theta? Rho squared sine of phi. Everyone agree? That's automatic. I have to put that down. Rho squared sine phi is the volume element for my d rho, d phi, d theta. Okay. Must put that. But it makes the problem way better. What's this though? You might know?
Right.
That's rho squared. Outstanding. So I'm going to put that right here. This, right through here, is represented by rho squared. So let me rewrite all this. What do I have now? A 12. Now I'm going to set up all my limits. Rho to the what? 4th. Sine phi, d rho, d phi, d theta. Now let's start with theta. What's theta? What's theta? 0 to 5. We haven't done this in a while. What's phi? D equals 0 up here. I'm going to go from phi there. Maybe I should use my markers.
Yeah, very good.
All right. Phi equals 0. Open it all the way up so you get the entire sphere. 0 to pi. What's rho? 2, 0 to 2, 0 to 2, 0 to 2. The radius was 2. Way easier than going Cartesian. We could have gone cylindrical coordinates. This is way easier than cylindrical coordinates. Can I split those up? I surely can. Haven't I got enough room right here? You got the 12. I'm going to do the integral from 0 to 2 pi. There are no thetas except for the d theta. I've got a integral from 0 to pi of sine phi. Then I got an integral of 0 to 2 of rho to the 4th. I'll just put a wall here. So this doesn't confuse you. What we're just doing. We're just going to take this over here and compute all that. Good. 12. What's that? 2 pi. What's the integral of sine? Cos or negative cos?
Negative cos.
Negative cos. All right, what's negative? Negative 1. Subtract negative 1. Lots of minuses in there.
3.
That's 2. That's 2. That's a 1 plus a 1, 2. And what's the integral of rho to the 5th? Rho to the 4th. Rho to the 5th over 5. From 0 to 2 is 32 over 5. So we got 32 over 5. We're going to multiply it 2. I'm going to multiply the 2 pi. And then I'm going to multiply that 12. That's that 2. That's that 2 pi. That's that 12. I'll just draw arrows so we can stay organized here. There's the 2. There's the 32 over 5. Go for the user calculator. What's 12 times 2 pi times a 2? That makes it what? 48 pi? What's 48 times 32 over 5? I'll let y'all hit it. And we'll write it in terms of pi. What do you get? Fill that in. In case you forgot. How much? Something pi. What's 48 times 32 over 5? Or I can do it. 48 times 32 fifths. Or I can just put 48 times 32 and put it over. 48 times 32. 1,536 pi over 5. There's the flux. That's the total flux across the entire surface. Isn't that cool? Okay. Divergence theorem. Hey, my next problem. I want you to think about something. What if you had to find a flux? Same surface. Same vector field. Okay? But I only want the top hemisphere, and there's no bottom to it. That's what I'm thinking about. I'll write it out. Can we still use this theorem somehow? In some way, can we use it? That's what I want you all to think about. Because when I do it directly, when I find a flux directly, it's kind of a pain, isn't it? So, I mean, this theorem makes it so smooth, so elegant, so easy. So my problem now is, well, what if you had just there?
Can I not divide it by 2?
But now, I want to make a note. It's got an open bottom. So what I mean is, don't do the flux off the bottom. So now it's an open surface. Okay. Now it's an open, so it's not the entire surface anymore. Top hemisphere. Center's at the origin, radius 2, oriented outwards. It's all oriented outward. So I just want the flux off this. Well, I guess I'll have to go back and do it directly. Or, can I do something? Any suggestions? What do you think?
Change the bounds of the phi, you know?
So I'll do that. But then when he's using Gauss in some way, I only have to change that, do you agree? So I'm going to do that right now. What would I go from? 0 to power 2. So far so good? Let me make sure I change them all. Change that. Change that. Change this. That changes this answer. What's negative cosine of pi over 2? Then minus negative cosine of 1. This becomes a what? A 1. So this just has to get divided by a what? A 2?
Mm-hmm.
I don't know. What is 1536 pi over 10? What's that become? I just took that last answer and divided it out with 2 from. What's that? 153.6? Probably go like that, right? 1536 pi or 153.6 pi. True? Okay. Or what would that be? What's 12 times 2 times 32? That would just be, let me do that. I'll write it that way everyone, so it's not a little bit simplified. 12 times 2 times 32, 768 pi over 5. Okay. So I got that. But that's not the answer, is it? Because what is this including? That's getting a flux off here. So by Gauss's theorem, we're including this. But I want to use Gauss's theorem because doing it the direct way takes forever. It's such a pain. Parameterizing the surface is a pain. Any suggestions what I can do with this answer to get that answer? What could I do? See, doing a flux just off a plain disk is pretty simple. So let's go back and just leave that answer right there. Let's go back and find the flux just off that disk outward and subtract it from this. We'll have the answer. Does that make sense?
Mm-hmm.
That's what we'll do. And I'm telling you, it'd be a lot faster than doing what? Parametrization of this surface by the other way. Because a flux off a flat disk is easy. What would be the unit vector going this way? I have to go this way because it originally had a flux outward, right?
Mm-hmm.
What would be a unit vector that way? 0, 0, 0, 0, negative 1. So what we'll do, leave this here, we're going to take this answer and we're going to subtract this flux. I can erase this. Take this all out. So Ellen, great job. Now let's just say, okay, right there, let me just draw an arrow. What will be your flux outward? But you can tell and that would mean it would be downward. From this disk. Oh. Let me draw a picture of that. It's a disk, it's in the XY plane. What's the radius? The radius is 2, right?
2.
Okay. So this is a disk with a radius of 2, and put your normal vectors up. So I'm just going to have to do this. Y dot our x cross our y dx. But you all just told me, you know what this is. What's this? 0, 0,
Negative 1.
negative 1. dy dx. Dot product. What's f composed of that surface? What's z equal to there?
0.
Z is 0. So when I'm going to write all this out, but for every z, I got to put a what?
0.
Now it's 0. So here it comes. 4x cubed plus 4y cubed. 4y cubed plus, I like this, 0. 4 times 0 plus a
4x cubed.
4x cubed. It looks long and sloppy, but look what you're dotting it with. Just a 0, 0, negative 1. What do you get? Just a negative 4x cubed dy dx. Now, do you want to stay Cartesian or do something else? We can't do a shortcut, it's got variables in here. It's a double integral, you wanna go polar? Okay, let's go polar. Go polar, woohoo! Alright, what's that in polar? That would be, what is x? Oh, I gotta put my automatic what? R theta? Do you remember what x was? R cosine theta, right? Okay, and I'm gonna keep that R in there. R cosine theta. So now you have, and I go from 0 to 2 pi, and what's the radius? 0 to
2.
2. Right, everyone, this was a hemisphere, radius 2 right there. Let me write this again. -4, 0 to 2 pi, 0 to 2, r to the 4th cosine cubed theta. And we would take this answer, and what would we do with this solution? From this.
Subtract it.
Take this and subtract it. Does that make sense? Take that answer right there, subtract this answer, you have it. Now if you want to compute this, you can. The cosine cube could become annoying now. You know, to integrate that, you have to use like trig substitution. What's sine squared equal to? A cosine squared is 1 minus what?
Science.
Sine squared. We can do that, but that's how we're going to take out that integral. But we'll do that. And I got enough room over there on that side, we'll compute it all. We'll deal with that cosine cube, and we're going to, in the end, take this, subtract this answer. If this is negative, I'll subtract it, but a subtraction of negative will be it, and we'll find the flux across that. Cool. I'm telling you, still, this would be a lot easier than working it just the other way. All right, let's find out. I'm going to break this up. I got enough room right here. -4, 0 to 2 pi. Cosine cubed, I can write that as what? Cosine squared is 1 minus sine squared times another cosine theta, right?
Mm-hmm.
There's the d theta, and oh, that r is going to be a piece of cake, everyone. Take that and multiply the integral from 0 to 2 of an r to the 4th. We'll do the easy r first. What's the integral of r to the 4th?
R to the 5th or 5.
R to the 5th over 5. I get 32 fixed. That was done. That was easy. It's this guy. Can you do a u sub for me with that?
Mm-hmm.
What would you let u equal to? First, I used a trig identity. So I could get that's a cosine squared times a cosine, giving me the cosine cube. What would you let u equal to?
Cosine theta?
I'm going to let the u equal to sine theta.
Okay.
And I'm way over here. You okay seeing that?
Uh-huh.
Oh, good. Shows up okay? U equals sine theta. Du equals cosine theta. D theta, look what happens.
Oh, yeah.
Whoop! You're gone. I'll keep that -4 there. You got the integral from 0 to 2 pi. You got a 1 minus u squared. Du. Not bad at all. So doing the integral of a cosine cube isn't too bad. Now what's the integral with respect to u? U minus what? U cubed over 3?
Mm-hmm.
Now put your u back. What was u? U was cosine of... No, u wasn't cosine. U was what? Sine theta minus sine cubed theta over 3. And we're going to go from 0 to 2 pi. I'll get this answer, and I'm going to multiply it to that 32 fifths. So I want to make sure you don't forget about that 32 fifths right there. Do all that, multiply that 32 fifths with R4. Take this, subtract it from that. I'll just work this out. Plug a 2 pi in there, what do you get? 0 minus 0. Nice. Minus, now put in zeros, what do you get?
0.
Put a bracket right here. Sit back and go. my gosh. This is interesting. What do y'all get? What do we got to subtract from that to get the flux off that?
0.
I know. And so, and you go, why is that happening? It's just the nature of this. This was where? This was located where z equals 0. And when you get here, everyone just get 0. So the answer to this, we're saying, take this, subtract the 0, and you got it. Awesome. Any questions on divergence theorem? And just to conclude this, when is that divergence theorem awesome? When is it great? It's awesome for closed surfaces. Spheres, cubes, spheres when you include the disks, a paraboloid, but it also includes the top portion like a disk capping it off, a cone, but there's a disk closing up the surface that way. Cool. And super job. Tomorrow, what we're going to do tomorrow is one last section. But I skipped over it. This was 69, it's going to be 16.8. Stokes theorem. And what we'll do is with this sheet, we'll just do those last 4 problems. Because they're set up nicely. Cool. Great job. Have a great day.